welcome back to Lecture 6 of Integral Transforms. We're going to finish off our coverage of the Laplace transform by talking about the two big theorems for it, the convolution theorem and the inversion theorem. So let's get straight on with it. The convolution is as near as you will get to the idea that you could take the Laplace transform of a product of functions. Now, you can't do that. In fact, that transform might not even exist, but there is something that is quite close, and that is called the convolution. So the convolution of two functions is defined by f and g, say. It's defined by taking f defined on the whole half line and g defined on the half line, and then you multiply together f of t, g of x minus t, and you integrate from 0 to x. So what is that? An easy way of thinking about this is in the context of probability. If x and y are two random variables which have positive values only, then the probability density of x plus y, independent random variables, the probability density of x plus y is given by exactly this formula here. So the probability that x plus y is equal to x is the sum of the probability that x is equal to t and y is equal to x minus t over all possible values of t running from 0 up to x. So this is actually quite a familiar object, and we'll be seeing a lot more of it later on when we do the Fourier transform as well. So that's the convolution, the integral from 0 to x, f of t, g of x minus t dt. It's very easy to show that f star g is equal to g star f, and you just put t minus x equal to u in the integral, and it all pops out. You'll notice in the notation here I put brackets around the f star g to make it clear that that is a single object and x is its argument. So this is a function of x, and the function is given by the recipe here. So let's see how it works for an example, very simple example. If x is 1, f is 1 and g is x, then what's their convolution? It's the integral f of t, well that's just 1. G of x minus t is x minus t, g of x is x, so g of x minus t is x minus t. And I integrate that from 0 to x, gives me xt minus a half t squared from 0 to x is equal to a half of x squared. And if you look at this, you may note that the Laplace transform of f bar, is 1 over p, 1 goes to 1 over p, x goes to 1 over p squared, and the transform of f star g, well that is a half of 2 over p cubed, a half there, transform of x squared is 2 over p cubed, and that's 1 over p cubed, which is the product of f bar and g bar. And this isn't a coincidence. This is our first illustration of the convolution theorem. Here's another example. Suppose that f and g are both equal to lambda e to the minus lambda x, where lambda is a positive constant and x is positive, of course. Then their convolution is, you get two factors of lambda up front, lambda squared, collect them there. F of t, lambda e to the minus lambda t, the lambda out front, g of x minus t, lambda e to the minus lambda x minus t, and that's lambda squared e to the minus lambda x comes out as a factor, and you're left with the integral of 1, which is lambda squared x e to the minus lambda x. And what this tells us in probability terms is that the sum of two IID exponential random variables is a gamma. So what are f bar and g bar? They're both equal to lambda over lambda plus p. Lambda is that number out front, and the 1 over lambda plus p is the Laplace transform of e to the minus lambda x. And then the transform of the convolution is lambda squared times the transform of x e to the minus lambda x. And that's lambda squared times minus d by dp of 1 over p plus lambda, and that's lambda squared over lambda plus p all squared, which is f bar g bar. So once again, we're illustrating the famous convolution theorem. And here it is. The Laplace convolution theorem says if f and g have Laplace transformed f bar and g bar, then the transform of the convolution is the product of the transforms. And this is as near as you will get to multiplication for the Laplace transform. So how do we prove this? It's actually quite simple. Let's start with the answer. Start with the right-hand side, f bar g bar, f bar of p, g bar of p. So there's f bar of p, integral of f of t, e to the minus pt. G bar, integral of g of s, e to the minus ps. We use a different variable, of course, so as not to get mixed up. This is a double integral, a very simple one because it's separable. Now we have p times s plus t in the exponent from that and that multiplying each other. Then what I do, the key step, first key step, is I put s plus t equals u. You might be a little uneasy about that because what we're really doing here is we're changing the variables in a double integral, and you should do that using a Jacobian and all that. So just think, if you have s plus t equal to u, and then you put t equal to v, you change from s and t to u and v, then the Jacobian is just 1, 1, 0, 1. The determinant of that is just 1. So, in fact, it is perfectly all right simply to do this, but it's a good idea to check that if you're at all unsure about it. So we put s plus t equal to u, and I get e to the minus pu here from the e to the minus ps plus t, and I get g of u minus t because s is u minus t. Look at the limits. The t limit is unchanged, 0 to infinity. The outer integral goes from 0 to infinity, but the inner one, now when s is equal to 0, u is equal to t, so u runs from t to infinity. And I don't know about you, but I always get confused at this point. I draw a little picture of the u-t plane. The inner integral u runs from t to infinity, so you imagine, how do you do integrals? You do little strips and you add up the values of the function at each little square in the strip, and then you add up the values of the strips going up. U runs from t to infinity, so the strips look like that, and then in the outer integral you add up all the strips like that. Now what we're going to do is we're going to swap the order so that our strips go from here to here, and then we add them up this way. So that says that our limits of integration on the inside are from 0 to t here, up that way, and then I run from 0 to infinity du, because I start with the very small strips down here, and then I add them all up over all values of u. So that's swapping the order. And then you see the point about swapping the order is that in the middle I have the integral of f of t, g of t minus u dt, times d to the minus pu du. And this is just the convolution of f and g with u as its argument and multiplied by e to the minus pu. So this is f star g, and that shouldn't be a u, that should be a p, of course, in there. F star g of p. You do need a theorem to do the swap of the order of integration. If it's Lebesgue integration, you'll use Frobenius theorem, but we're not going to worry about technicalities of that kind in this course. All right, here's an example, very simple example. Find f of x satisfying f double prime plus f equal g of x, where x runs from 0 to infinity with 0 initial condition. So this is a simple harmonic oscillator, f double prime plus f, with an input term on the right-hand side, a forcing term on the right-hand side. So what do? You take the Laplace transform in x, and you get p squared f bar minus 0 from these initial conditions here, from the transform of f double prime, plus f bar equals g bar. So f bar is just g bar over p squared plus 1. But we know what p1 over p squared plus 1 is. It's the Laplace transform of sine x. So that says f of x is the integral 0 to x, g of t, sine of x minus t dt, which is the convolution of g and sine. Another example. We're going to go back to the heat equation example that we had at the end of the last lecture, 53D I think it was called. And that was the first example which you couldn't do by elementary methods. In fact, you can do that example by looking for a solution of the problem u of x and t in the form a single function of a single variable v of x divided by the square root of t, and then using the simple chain rule in the differential equation and in the boundary conditions. And if you do that, you will find that you can solve the problem exactly. It's what's known as a similarity solution, and they're covered in one of the later courses on applied partial differential equations later on in the course. I should say known, shouldn't it? Funny how when you're giving a lecture you notice all the little mistakes that you don't notice when you're typing and proofreading. Anyway, that should say known. Alright, so what was the problem? It was the heat equation, du by dt, dtu by dx squared, x and t both positive. You start off with 0 initial temperature, and you put on a temperature f of t at the left-hand end, x equals 0, so u of 0 and t is f of t. And then what you want is the relationship between the boundary heat flux, which is minus du by dx, evaluated at x equals 0, that's what we call g of t, and the boundary temperature f of t. And previously we took f equal to 1, but now we're going to apply a general temperature, and we're going to say what's the relation between the boundary temperature and the boundary heat flux. So you can imagine this, for example, if you just wanted to work out what is the relationship between the temperature at the surface of the Earth and the heat flux in from the sun in a really, really simple model, you would write down exactly this problem with 0 representing some average temperature, and then you would apply a periodic temperature f of t, and you would say what is the heat flux in, well, you'd apply a periodic heat flux g of t, and you'd say what is the surface temperature f of t. Of course, that's a great simplification of a much more complicated situation. You should really have radiation and all sorts going out from the Earth, but nonetheless, it's the basis of a very, very simple model. And it's a really nice mathematical problem too. Here's how you solve it. We take the Laplace transform in time as before, so u bar is the integral of u of x and t e to the minus pt dt. So x and t become x and p as the variables. P is really a parameter. And we have pu bar minus a 0 term, so that pu bar is d2u by dx squared, with u bar of 0, and p is the transform of the boundary data f bar of p, and earlier on we had f bar equal to 1 over p, which is the transform of 1. So u bar of x and p is very easy to solve. It's just f bar of p e to the minus x root p. The root p comes from solving this constant coefficient equation. It's constant coefficient as far as x is concerned, because p is just a parameter, and the solutions are e to the plus or minus x root p, but you throw away the exponentially growing one. Now we differentiate with respect to x. We take du bar by dx, which is g bar of p, the Laplace transform of minus du bar by dx. So we just differentiate this with respect to x, and what happens, we get a minus sign, which kills the minus sign outside. We get a root p from the exponent, and the f bar of p is, of course, independent of x. So we get root p f bar of p e to the minus x root p. X equals 0 gives g bar is root p f bar. So f bar is g bar over root p. But we know what 1 over root p is the Laplace transform. It's the transform of 1 over the square root of pi t. That pi was a gamma over half, or the root pi was a gamma over half. So if you use the convolution theorem straight away, f of t is the convolution of g and 1 over root pi t, which is 1 over root pi, the integral 0 to t, g of s ds over root t minus s. So g of s is the function we're taking the convolution with, and we replace the argument t here with t minus s. I could do it the other way around, of course, but this is the convenient way to look at it. So, given g, given the heat flux, I can now just calculate what F is. But what if I wanted to find G from F? In other words, I give you the temperature and I say, what's the heat flux? Which is what we did before, actually. So that amounts to saying, if I know what F is, calculate G from this equation. It's an integral equation, not a differential equation, an integral equation in which the unknown function is multiplied by a kernel, 1 over root t minus s, and then integrated. So there's a really neat trick. What you do is you go back to the previous line where we had g bar is equal to root p f bar. G bar is root p f bar. And we write that as g bar. We split this root p as p divided by root p. That's the trick. So p over root p f bar. And then we say, okay, we know what p f bar is. P f bar is what we see when we take the transform of the derivative of f. We take the transform of f prime, we get p f bar minus f of 0. So p f bar is the transform, is f of 0 plus the transform of f prime. And that means, therefore, that g bar is f of 0 over root p plus f primed bar over root p. And now we can just apply the result we had before. G is f of 0 over root pi t. That 1 over root pi t is the, that 1 over root pi t is the inverse of 1 over root p. And then 1 over root pi, this is just the convolution. 1 over root pi, the integral 0 to t, f of s over root t minus s is just the convolution of 1 over root pi t, which gave us this root p on the bottom, and f primed of s on the top. And you might like to think, what is the physical interpretation of this term, and what is the physical interpretation of this term? This whole result is known as Duhamel's theorem. Okay, so now we're going to move on, and we're going to state two absolutely key theorems about determining a function from the Laplace transform. The first one says if f is continuous and doesn't grow too fast, doesn't grow more than exponentially, then if its transform is 0, then f is 0. And by extension, if you have two functions with the same transform, then subtracting them, their difference is 0. And what that tells you is that the Laplace transform determines the function uniquely. So that's the theorem that we've implicitly been relying on all along when we've been saying this is the transform, therefore that is the function. We've been assuming that this kind of uniqueness result applies. And then theorem 64, this is the famous Laplace inversion theorem, and what it does is it gives you a formula from which you can determine the function given the Laplace transform. So if I know f bar, f of x is given by this formula here, so we need to take this to pieces and have a look and see what it says. Suppose f is continuous and has Laplace transform f bar for real part of p greater than p0. So this is the usual setup, we know all about that. Then for x greater than 0, f of x is given by the contour integral representation. F of x is 1 over 2 pi I. It tells us immediately we're doing a contour integral. The integral from sigma minus I infinity to sigma plus I infinity. We'll see a picture of this in a moment. But this says we take a contour which starts at minus infinity in the imaginary direction, and with the real part of p, we're integrating with respect to p, the real part of p equal to some value sigma, which just has to be anywhere you like to the right of p0. So you start at minus I infinity, and you go straight up to plus I infinity in a straight line. F bar of p, now where you had e to the minus px, you now have e to the px, and you could perhaps have guessed that that was what was going to crop up, that if f bar had an e to the minus px in its definition, then f is going to have an e to the px, and now the integral is with respect to p, of course, not with respect to x. The precise value of sigma is unimportant because by the deformation theorem you can move this contour to the left and to the right as far as you like, as long as you don't cross the real part of p equal to p0. So that's the formula. Now we're not going to give a precise proof of it. We're going to see a really neat proof of it when we do the Fourier inversion theorem in a couple of lectures' time. So we're only going to give a sketch. I should have said, incidentally, that the proof of the uniqueness theorem is given in the lecture notes, and we're not going to look at that here. The proof of the inversion theorem is also given in the lecture notes for a very special case in which the f bar, the transform, is a rational function. It has to be a rational function. It's a ratio of two polynomials. The degree of the one on top has to be less than the degree of the one on the bottom, so we have decay at infinity. And we assume it has a single pole because you can imagine when there are more than one pole, you deal with them all separately in a classic contour integration kind of way. This, of course, is only a special category of transforms, and it doesn't include a lot of the standard ones, but it gives you a little bit of a flavour. So f bar had the form g of p over p to the n, where g is a polynomial of degree less than n. So what are the key steps? The first key step is that you close the contour, as you always do in contour integration, and you go to the left. And why do you go to the left? Because in the integral, you're looking at a factor of e to the px. X is going to be positive, so you need the real part of p to be negative, so that you get exponential decay from that e to the px term on the semicircle. So you close on the left with a semicircle. You use the Jordan lemma, which lets you handle contour integrals of that kind to show that the contribution from the semicircle goes to 0 in the limit. Then you use the residue theorem to pick up the residue at the origin, and the rest is a rather intricate little calculation which just says you combine the formula for the residue of a pole and the Leibniz rule to show that the Laplace transform of the integral is exactly f bar, and so the integral must be equal to f. It's a slightly awkward proof, I have to say, and as I say, we are going to see a far better one later on, so we're not going to spend too much time. Do read the proof in the lecture notes because it is something you ought to see, but we're going to see a far better version of it a little bit later on. Right, that's a good time for you to take your 20-20-20 break. We're going to come back with some examples to round off this lecture. I'll pause for a moment. Okay, so simple example, invert f bar of p is 1 over p squared plus 1. Now, of course, you know what the answer is. It's sine x. And you can do it by partial fractions, and in any case, you know the answer. But we're going to do this as if we didn't know that. So we look at the function e to the px over p squared plus 1. Now down here, this is the p plane, the real part of p, the imaginary part of p. This function has poles at p equal to plus or minus I. And they're there, they're a little bit faint, but they're there, one there at minus I and one there at plus I. This sigma here showed that our inversion contour starts at minus I infinity down here, sigma minus I infinity goes up the axis and go to sigma plus I infinity, up parallel to the axis, not on it, but parallel to it, to the right. And then you close with a semicircle like this, and you pick up the residue contributions from minus I and from I. We work out those residues. They're very easy ones. E to the px at p over p squared plus 1. You just differentiate the denominator to give you 2p, and then you set p equal to plus or minus I, and you have e to the plus or minus ix over plus or minus 2i, and those are the residues. And so f of x is 1 over 2 pi I multiplied by 2 pi I times the sum of the residues, and there they are added up, and that's just sine x with these terms out front cancelling. Here's another example. Invert p to the minus a half. Well, we also know the answer here. It's defined as r to the minus a half e to the minus I theta by 2. So what we're doing is we're saying with theta between minus pi and pi, so we're putting the branch cut along the negative real p axis, like that, along there, and then we're taking the principal branch, which is the one that is positive on the real axis when theta is equal to 0, so that's the plus root, if you like. And because you're not allowed to cross this contour, the function e to the px times p to the minus a half is not holomorphic on the branch cut or at the origin. What you do is you take your inversion contour here, is to the right of all the singularities of p to the minus a half. You go up there, you come down a quarter circle, you have to come in along the top of the real axis, round the origin, back along the bottom of the negative real axis, and then you finish your semicircle like this. So there's a certain amount of technical work to do. You need to show, and you'll see in the lecture notes how to do it for a slightly different example. You need to show that the integral around these arcs go to 0, and then you use Cauchy's theorem to say that the integral around the whole lot is 0, because there are no singularities inside the contour, no poles. And that says, therefore, that the integral we want from A to B in the diagram, from there to there, is equal to the integral from C to O plus the integral from O to D plus the two contributions that vanish in the limit. Now you need to be a bit careful. On CO, you put P as R e to the I pi, because theta is equal to pi. Remember, theta runs from minus pi on the bottom of the branch cut all the way around to pi on the top of it. So we put P as R e to the I pi, P to the minus a half is R to the minus a half e to the I pi by 2, which is I R to the minus a half. And on the bottom you put P as R e to the minus I pi, so you get minus I R to the minus a half. And so when you let R tend to infinity, the integral from C to O becomes the integral from infinity to 0 of R to the minus a half, and then P is equal to minus R, so you get minus e to the minus Rx times, and you'll notice that that is exponentially decaying, good. Then you have minus dr, that's the dp is equal to minus dr. Now you swap the limits, and that gives you the integral of R to the minus a half e to the minus Rx dr from 0 to infinity, and that's minus 1 over 2 pi x to the minus half gamma over half. And similarly, the other one gives you exactly the same thing, and so when you add them all up, the integral we want plus plus that one is equal to 0. So the integral we want is equal to this one plus this one without the minus signs. And that's twice over 2 pi x to the minus a half gamma over half. Gamma over half is root pi, so you get root pi over pi x to the minus a half, which is exactly as we expected, 1 over root pi x to the minus a half. Quite hard work doing it that way, but if you didn't know, that's how you could do it. Now, one of the great things about the Laplace transform is that you can apply it term by term to power series, or you can go the other way around and you can say if your Laplace transform is given by a power series, then you can recover the function as a power series as well. And the theorem that tells you this says if f bar of p is the sum of an over p to the n plus 1, and the particular form here chosen because we know that the inverse of p to the n plus 1 is 1 over p to the n plus 1, has to do with x to the n. So if f bar of p is given in this form, then f of x is the sum of an x to the n divided by n factorial. So the proof of this is in the lecture notes, and the only reason that you even have to worry much about the proof is you have to be able to swap the summation and the contour integral. It's a little technical matter. We're not going to get into that level of detail, but believe me, it can be done. But the key to it is the result that the Laplace transform of x to the n is n factorial over p to the n plus 1. So 1 over p to the n plus 1 becomes x to the n over n factorial when you invert. Just incidentally, you'll recognize that this is actually a Laurent series. So although it will converge for the real part of p large enough because it's a Laplace transform, in fact it will converge for the modulus of p greater than p naught, because it's a Laurent series, and you know a Laurent series, if it converges at all, it converges on an annulus. And that means that all the singularities of f bar must lie within this annulus, mod p equals rho 0, in this case within a disk, and so it wouldn't cover, for example, p to the minus a half. Nonetheless, we're going to see a nice application of this in just a moment. Here's a simple one. Take the function 1 over p minus 1. Well, of course, you know what the answer is if you invert that. Pretend we didn't for a minute. 1 over p minus 1. We want to expand this for large p. So we have to first of all take a factor of p out of the bottom. So that then becomes p times 1 minus 1 over p. 1 over p is going to be small as p goes to infinity. And so this is 1 over p, the sum of 1 over p to the n by the binomial theorem, which is the sum of 1 over p to the n plus 1. And therefore f of x is the sum of x to the n over n factorial, because all the an's are equal to 1, which of course is just e to the x. So we're going to finish off on the Laplace transform with an example that brings together pretty much all the ideas that we've seen so far. And this concerns the famous Bessel function of order 0, known as J0 of x. And J0 of x is one of those functions that crops up all over the place. It is, as it were, the next most complicated special function after the trigonometric functions. And it's the solution of the differential equation x J0 double prime plus J0 prime plus x J0 equals 0. Now, if you didn't have that term in the middle, if you didn't have the J0 prime, you could cancel the x and you would have simple harmonic motion. So if you imagine now dividing by x, you would have simple harmonic motion, J0 double prime plus J0 plus J0 prime over x. This is looking a little bit like a damping term, but the damping term depends on position because there would be a 1 over x here. So this is going to look a little bit like a damped harmonic equation, but because the damping depends on position, the function itself isn't periodic. It becomes close to periodic as x goes to infinity and its amplitude decays, or it becomes close to an exponential decay multiplying by a decaying periodic function, I should say, not exponential, but it isn't exactly periodic. The commonest place you would find it, the sort of easiest way to visualize it, is if you take the wave equation in 2 dimensions and then look for radially symmetric solutions. So you might, as it were, have a drum, a circular drum, and you look for radially symmetric oscillations of it. And the equation of motion of a 2-dimensional drum is d2u by dt squared is c squared times the Laplacian of u, del squared u. But the radial symmetric version of that is d2u by dr squared plus 1 over r du by dr. If you look for time harmonic solutions of this, you will fairly shortly find that you can get to this equation by a simple change of variables. And the roots of J0 tell you the fundamental frequencies of a drum. Anyway, that's all just letting you know that J0 is a very common and important function. It has some initial conditions. J0 of 0 is 1, J0 primed of 0 is 0. So this just normalizes it. The equation is linear, of course, so you could take any multiple, but this just picks it out as the solution that is 1 at the origin. So let's take the Laplace transform of the differential equation. X J0 prime double prime plus J0 prime plus X J0 is 0 with the boundary conditions. So the J0 prime double prime bit, the X here gives minus d by dp. J0 double prime gives you p squared J0 bar minus p. That p is p times this 1 here. And then the J0 prime gives you p J0 bar minus 1. And the x J0 gives you minus dj0 bar by dp, all equal to 0. And if you tidy that up, you find p squared plus 1 dj0 bar by dp plus pj0 bar is equal to 0. With the 1 cancelling, you can see the d by dp of p and the 1 go away. So a differential equation has become a differential equation. But at least this one is simple. It's first order and it's separable, or indeed do it by an integrating factor, but it's easier to separate it. In other words, dj by dp over j is equal to minus p over p squared plus 1. And then that gives you straight away that J0 bar is a constant. A is a constant over the square root of p squared plus 1. But what is A? Somehow we thought we would have known A, we would have found A along the way. Well, there's a trick to do that. What we know is that J0 bar goes to infinity. J0 bar goes to 0 as P goes to infinity. Well, that's true. You can see there's a 1 over root P squared plus 1. But it should also be true that the transform of the derivative J0 primed bar should also go to 0 as P goes to infinity. And what is J0 primed bar? Well, that's P J0 bar minus 1, which is P times A over root P squared plus 1, or A times P over root P squared plus 1 minus 1. And that's got to go to 0. This lot goes to 1, and so A must be equal to 1 so that this can go to 0 at infinity. So J0 bar is 1 over the square root of P squared plus 1. Now we'll find its power series. There are other ways of doing this, but there's none that are as simple as this. We have J0 bar of P is P squared plus 1 to the minus a half. Write it this way because we're going to use the binomial theorem to expand this. As before, we need to expand for large P, so we take out a factor of P squared from the inside, becomes a P in the denominator, 1 over P there, times 1 plus 1 over P squared to the minus a half. And this is 1 over P, so this is just the binomial expansion. We get a minus a half, minus 3 halves, minus 5 halves, blah, 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 minus 1 minus 2k over 2, 1 over P squared to the power k, and k factorial on the bottom, so that's just applying the straightforward binomial theorem. Now you stare at that for a little bit and you realize that if you multiply the top and bottom by k factorial, you can, and by 2 to the power 2k, what you have here are 1, 3, 5, 7, 9 up to 1, 2k minus 1 with a minus 1 to the k in front. And if you put the even numbers in, that's where the extra k factorial comes from. And that makes this into a 2k factorial on top and k factorial squared on the bottom. In other words, the other k factorial on the bottom is cancelling with all the even numbers in this product. And then you have 1 over P to the power 2k plus 1, which is that 1 over P there, and this 1 over P to the power 2k. Now we know that 2k factorial over P to the 2k plus 1 is the transform of x to the 2k, so there is the power series for J0 of x, the sum of minus 1 to the k, 2 to the 2k, k factorial squared, x to the 2k. And we were going to end with a really neat little result. This is cute. If you start with J0 bar of P was 1 over the root of P squared plus 1, and you square it, you get 1 over P squared plus 1. But we know that. It's the transform of sine x. And therefore, by the convolution theorem, J0 bar squared is the transform of J0 bar of J0 star J0 star J0. So the convolution of J0 with itself is, of all things, sine x. Completely unexpected. J0 is really nothing to do with sine x. It looks in a vague sense a bit like a trig function, but only a very vague sense. And then all of a sudden, a result like that comes up. That's why we get out of bed in the morning. It's a beautiful result with which to end our coverage of the Laplace transform. We're going to move on in the next lecture, and we're going to start work on the Fourier transform, which is, I have to say, the mathematically most far-reaching and important and deep part of the course. We have only time to scratch the surface, but for the last 3 lectures of the course, there's something to look forward to. So I'll see you then. Bye.